So, warm welcome to the 23rd lecture on the subject of digital signal processing and its applications. We use this lecture to discuss the solution to the mid-semester examination that was conducted in this course. Of course, the detailed solution is available on the course web page, but it is useful to discuss the questions and their answers, the instructor's solution and the possible variants, more than from the point of view of evaluation, from the point of view of understanding some niceties, some finer points in the material that was studied. So, more than just looking at the evaluation aspect, which of course has been done routinely, it is important to understand some finer ideas that were being communicated through the questions that were asked in the mid-semester examination. So, what I shall do in this lecture is to present the question first and then discuss the instructor's solution to it, and then of course ask for any clarifications if there are any questions or clarifications that have to be made. Now, so you see we are going to look at now we look at the first question. I shall project the relevant question, or I shall briefly explain the question and then give its response. So, the first question, I will just mention the main points. Of course, we load the question paper and the instructor solution on the web page, but we will put the main points here. So, we do not intend to discuss every step of the solution, but we wish to discuss some important or salient points of the solution which are important from the point of view of concept. So, here we go for the first question here. The first question was whether the system, now in all the questions, in all the parts in the question number 1, we use xn to denote the input of the system and yn to denote the output. And therefore, the question was, does this describe a causal system? And of course, the answer is yes. That is because although this is n plus 1, that was the deceptive part, this is n plus 1, that does not affect the causality. The causality only relates to the fact that y of n depends on the current sample of x and on no other. It does not matter what function you perform on the index before you apply that to the sample. That does not affect causality. So, the system was indeed causal. Question 1, part 2, part B, asked whether y of n is equal to n times x of n is a bounded input, bounded output stable system. And the answer is no. That is because you could give a counter example by taking y of n is equal to u of n. This is bounded, but the output is clearly unbounded. So, you have a bounded input with an unbounded output, and that serves as a counter example. If there are any questions, please pose them right then and there. So, question 1, part C, asked whether in a Bibo unstable system, does an unbounded input necessarily produce an unbounded output? And the answer is no. You see, in an unstable system, you are guaranteed that there is at least one bounded input which produces an unbounded output, but you are not guaranteed either that every bounded input produces an unbounded output or that an unbounded input necessarily produces an unbounded output. In fact, we can give a very simple counter example by exploiting the Z transform. So, you see, if you take the system, if you take this system, if you take this input 1 minus 2z, I mean I am showing the z transform of the input. And if you consider this system, the system with system function 1 minus 3 z inverse by 1 minus 2 z inverse mod z greater than 2. Clearly, this input is unbounded, the system is unstable. But when you find the output, it is essentially an impulse. And of course, you do have a valid region of convergence. So, you have at least mod z greater than 3 as a region of convergence. And therefore, if you take the inverse z transform of this xz as the input and the inverse and this as the system, which is clearly unstable, then this input applied, this system is clearly Bibo unstable, this input is unbounded. That is clear because if you look at this is essentially an exponential with a factor of 3, alright. The output is however going to be an impulse. Now this is of course just one counter example. You are welcome to give any other counter example, but in general you are not guaranteed, it shows that you are not, that's a very tricky thing, you are not guaranteed that a Bibo unstable system gives an unbounded output when the input is unbounded. Yes. So you see what is the region of convergence? At least mod z greater than 3. So the question is why were we taking mod z greater than 3? So the answer is that you see the region of convergence is at least the intersection, if not more, right. So here we are sure that there is some part in the region of convergence. Mod z greater than 3 is the minimum part. Of course, the region of convergence may expand. In this case, it does. In this case, in fact, the region of convergence goes all over the z plane. But we are sure that there is a region of convergence to begin with. So maybe what we should say is mod z greater than 3 at least is the region of convergence. So we have something to begin with. Alright. Now question 1, part 4. So the question is, in the previous system where you had y of n is n times x of n, could you have given a bounded input which produced a bounded output? Yes, indeed. So for example, if you give xn equal to delta n, the unit impulse, it produces a bounded output. In fact, it produces all 0. So in an unstable system, it's not necessary that every bounded input produces an unbounded output. But there is at least one bounded input which produces an unbounded output. This illustrates the idea. So question 1d was, if you give a Bibo stable system, the input x of n is minus 1 for n odd and 1 for even n. Is the output bounded? And of course, the answer is yes. That's because it's a Bibo stable system, the input is bounded by 1 and therefore the output must be bounded. So that's simple. On the other hand, in question 1 part E, you are asked whether a linear system responds to the standard. You see, you are told that delta n produces some output Hn which has a finite number of finite samples. System is linear. Now, the statement was that if you give a bounded input, would it produce a bounded output in general? And the answer, of course, is not necessarily. That's because you are not told the system is shift invariant. So, although the impulse located at 0 produces a finite number of finite samples, the impulse located somewhere else might not. And in fact, not just the impulse, some other combination might not. And in particular, of course, for a linear system, you can use impulses located at various places to see what the system does. So it's quite possible that the input located somewhere else may not, and then you have trouble. So it's not necessary. So the answer is no, it's not correct. So much so for question 1. Now, are there any doubts or difficulties about question 1 beyond this? Yes, please.
The only point is that some other shifted impulse it will be giving a response which is like an unbounded.
Yes. So the question asked is, in the part E of question 1 was the point that if the impulse were located elsewhere, there could be an unbounded output. And the answer is yes. The system being linear but not shift invariant could have a different response to an impulse located somewhere else, and that could be unbounded. Now we come to question 2. You are given the response to delta n minus k for k over the set of integers. You are told that for k less than 0, the output is all 0. For k equal to 0 and 1, the output is given. So, we will quickly put them down. K less than 0, all 0. K equal to 0, 1, it is Gn minus k, and Hn minus k, and Hn is specified to be 1, 2, 1 with this 1 placed at 0. And for k greater than 1, it is Gn minus k, and Gn is specified to be 1, 2, 2, 1 with this 1 located at 0. So, the first question is to write down the output yn in terms of the input xn in general. Now, you see, when a system is linear, of course, any input can be written in terms of the impulses. This is true for any input. And if the system is linear, then one thing is clear, yn is summation over all k, xk is like a constant here. So, xk responds to delta n minus k. This is true because the system is linear. So, on account of additivity, you can take the response over each of these, and on account of homogeneity, you can take the response into the xk. And therefore, we can now write down yn in terms of all the responses to different impulses. That is true for any linear system. The only catch is that for a linear system which is not shift invariant, this cannot be written in terms of a single Hn. Now, this question was meant to test one's understanding of the proof that LSI systems have an impulse response that characterizes them completely. So, the system is linear but not shift invariant. What is it that is required to characterize? So, one dilutes the proof, so to speak, to come to a weaker requirement. So, it is meant, you see, I used to stress in the class that it is not enough simply to understand the proof, but also appreciate all its variants. And that means one must learn to read between the lines in what one is doing in the classroom. So, you see, that was what was being tested in this question, and that is of course going to be true in the future as well. Unless you learn to look beyond simply what is said obviously in the class, it will not enable you to understand the subject in depth. Now, one can work this out, and one can show that in general this is the response that you get. Yn is in general 0 for n less than 0, x of 0 for n equal to 0, twice x of 0 plus x of 1 for n equal to 1. So, you can expand this, you can expand this output and get, so I am just putting down the response, x1 plus twice x2 plus x3 for, x0 plus twice x1 plus x2 for n equal to 2. And we can continue this. It is equal to x1 plus twice x2 plus x3 for n equal to 3. Twice x2 plus twice x3. So, you see, it is clearly shift variant, the behavior changes. for n equal to 4. And again for n equal to 5 you need to write a separate expression, and beyond that you can write a common expression. x5 plus twice x4 plus twice x3 plus x2 for n equal to 5. Up to 5 you have to write separate expressions, and beyond that of course one can write xk plus twice xk minus 1 plus twice xk minus 2 plus xk minus 3 for n greater than 5. Now of course this expression also holds for 5, and you may therefore take it from 5 onwards. Now this follows by adding the individual responses to different impulses, right. So I leave it to you to work out the details, but the idea is that in such a linear shift variance system you need to write down the output at every point in terms of the input samples, and from here you can also see that for some samples there could be a combination of a fewer number of input samples and for some more. And this is what was also discussed in question 1, in one of the questions where the system was not shift invariant. So, it could be possible that for one impulse located at one place, you may have a finite length response, and for another place the response may be of infinite length. That can happen if the system is not shift invariant. So this is in general the expression. Now of course the next part of the question was to write down the output for a specific input. And the specific input was this, and of course one can simply substitute and one can get the following expression. So this is for that specific input, right? One just substitutes the values of x0, x1, x2 and puts them in the respective samples to get the output. Now, question 2 part C was to answer whether the system was causal. And of course, the answer is yes indeed. That is because if you look at the expression for yn in terms of xn, every sample involved either the current sample or past. Future samples were never involved, and therefore one could see that the system was causal. Okay. The next part was to answer whether the system is stable, and of course the answer is again yes. Luckily in this particular system, every output sample was a combination only of a finite number of input samples, albeit different at different places. And if the input was bounded, then you would have a finite combination of bounded samples, and therefore the output needed to be bounded everywhere. So the system was stable. Now, if there are any questions on this, then we can answer them before we proceed to question 3. All right, since there are no questions, we will proceed to question 3. Now, in question 3, there were two objectives, and the question was as follows. You were given a real impulse response, rational LSI system. Well, not necessarily rational actually, I am sorry. Stable LSI system. So you have a real impulse response and you have a stable LSI system. So you are bound to have a frequency response. So the frequency response is guaranteed to exist. Not only that, the frequency response is going to be magnitude symmetric and phase antisymmetric. That is because the frequency response is conjugate symmetric. So the magnitude is symmetric and the phase antisymmetric. And you were given the magnitude in the range 0.45 pi. So you see the magnitude between you were only given the magnitude between 0.45 and 0.55 pi, and you were told the magnitude is constant at B. And we were told that the phase is essentially a linear phase. Well, if not, one wouldn't call it linear, actually one should call it pseudo-linear. Pseudo-linear because it does have a straight line expression, but it does not pass through the origin. So, it is a phase like this, it is a straight line kind of function. And the phase response was specified to be minus tau p omega 0 minus omega 0 times tau g, where tau p and tau g are positive constants. And omega 0 is called the center, omega 0 is also a positive constant called the center frequency. Now, you see, you were told to consider a combination of two sinusoids. In fact, the input given was of this nature. Now, product of sinusoids is always expressible as a sum of two sinusoids. So, it is cos omega naught plus omega 1 times n plus cos omega naught minus omega 1 times n. So, a product of two sinusoids which was given to be the input is actually a sum of two sinusoids as well, with frequencies omega naught plus omega 1 and omega naught minus omega 1. Now, you see, you were also told that omega naught plus omega 1 is strictly less than 0.55 pi, and you were told that this is greater than 0.45 pi. What it really says is that these two sinusoids are well within the band of interest. So, you are in a position to use the frequency response to find out the output, and of course, the system is linear and shift invariant. The input is a sum of two sine waves, so you can find the output by using the frequency response. That's the idea here. Now, one can easily calculate the output in this case by using the frequency response, and we have here the output is going to see. So, essentially the input is the sum of two sine waves, the output is the sum of individual responses to each of these sine waves. So, cos omega naught plus omega 1 times n and cos omega naught minus omega 1 times n, and you are guaranteed that they lie within the band in which the frequency response is specified. Now, I must again stress that here you do not need to worry about the frequency response on the negative side of omega, because it is going to be conjugate symmetric. That is given, that the impulse response is real. So, therefore, the output turns out to be A B by 2. So, you see the cos omega naught minus omega n responds with cos omega naught minus omega 1 n minus, you see, this is the change of magnitude and this is the change of phase. For the omega naught minus omega 1 frequency, essentially you are multiplying the magnitude by b and you are adding the phase of, as given, minus tau p omega naught minus, in place of omega we put omega naught minus omega 1 and of course minus omega naught times tau g. So, there we are. And for the and it is equal to AB by 2 times cosine omega naught plus omega 1 n minus tau p omega naught minus omega naught plus omega 1 minus omega naught times tau g. For the omega naught plus omega 1 frequency. So, here you have again multiplied the magnitude by 2 and you have added a phase of minus tau p omega naught minus, now in place of omega you have put omega naught plus omega 1, so omega naught plus omega 1 minus omega naught times tau g. So, you see when you add these two terms, what you get is the following. The output is AB by 2 cos omega naught into n minus tau p plus omega 1 into n minus tau g plus cos, in fact you can take all this in the bracket, cos omega naught n minus tau p minus omega 1 into n minus tau g. So, again it is a sum of two sinusoids as expected. The catch is that you have a very interesting change of the time. There is a different change of time on omega 1 and on omega naught. That is very interesting. So, you can combine. Now, you can put this back in, you were asked, actually it was asked to express as a product of sinusoids. And that would of course give you AB cos omega naught into n minus tau p times cos omega 1 n minus tau g. Now, we need to interpret this. It is very interesting. We had a product of two sinusoids initially of frequencies omega naught and omega 1. And you know, one is assuming here, or even though it is not explicitly said in the question, let us take the situation where omega naught is considerably larger than omega 1. So, to take an example, omega naught could be 0.5 pi. Here in this, it must be in the range, it has to, you see, because omega naught minus omega 1 and omega naught plus omega 1 are both in the range 0.45 to 0.55 pi. So, the omega naught has no choice but to be inside that range. Let us take it to be 0.5 pi. And let us take omega 1 to be, let us say, 0.01 pi, right. So, it is much smaller than omega naught. Now, this is like a situation where you have what is called amplitude modulation for communication, for those of us who are familiar with that. In any case, you have a very low frequency sine wave multiplying a high frequency sine wave in that case. In communication, this is called amplitude modulation. So, you change the amplitude very slowly in accordance with the message, and here the message can be taken to be of frequency omega 1, and the carrier which carries the message is of frequency omega naught. And what we have done is to take a pseudo linear phase. What I mean by a pseudo linear phase is you have taken the phase to be approximated by a straight line around the carrier. Now, what do you mean by approximating a phase by a straight line? You see, if you have a very small band signal, a very narrow band signal around the carrier, and if the phase is continuous and the magnitude non-zero, you see, if you are taking the signal to be very narrow band compared to the center frequency of the carrier. So, in that narrow band, if the frequency response is analytic at that point, then you may make a Taylor series approximation. And if the magnitude, if you are not operating on what is called a transition band region, that is important. You should not be operating on a transition band. If you are operating somewhere in the pass band, you can assume that the magnitude response does not change too much. around the carrier if it is narrow band. And the phase response, even though it may change, if it is analytic in that region, you may approximate it by a Taylor series with only the first term. That is what you are essentially saying. So, take a Taylor series approximation of the phase with only the first term. That is what we have done here. Now, what it shows is that in that circumstance, there are two delays. You see, the first term of the Taylor series, how do you construct the first term of the Taylor series? The value of the function. So, you go back to the expression that we wrote for the phase right in the beginning. So, the expression for the phase has a constant term here and a term which varies omega, you are writing a Taylor series expansion around omega equal to omega 0. So, this is the first term of the Taylor series. So, this is essentially the derivative of the phase, and this is the 0th term or the constant term in the Taylor series, which is essentially the value of the function at that point. So, when you take, you can always divide that value by omega naught and call that tau p. So, the phase at omega naught divided by omega naught is called the phase delay, and the derivative of the phase at omega equal to omega naught is called the group delay. And the significance of the group delay is that it acts on the message, and the significance of the phase delay is that it acts on the carrier. That is what we have been able to demonstrate by this question here. Now, here we demonstrated it exactly when you took a message which was exactly a sinusoid, a very narrow band message which is a sinusoid. But you could of course extend this idea if the message had a combination of sinusoids but narrow band. So, the aim of this question was to illustrate through a very closed process, through a very guided process, the meaning of group delay and phase delay when you have a phase response. We had been saying at some stage the phase response is a necessary evil, and what this illustrates is the precise effect that the phase response has when you have a narrow band message operating on a high frequency carrier. Are there any questions on this? So, if there are none, we can then take the next question, question 3b. Now, question 3b gave you the sequence x of n. The sequence was given, and you are required to evaluate the integral from minus pi to pi mod x omega squared d omega. Of course, this is easy to do. One can use the Parseval theorem for doing it, because you know that mod xn squared summed over all n is 1 by 2 pi integral minus pi to pi mod x omega squared d omega. So, you don't. So, the idea was without evaluating the discrete time Fourier transform, you were required to find this quantity, which is easy to do because you could take 2 pi to the other side and you are done. Similarly, you were asked to evaluate the quantity integral of x omega with respect to omega from minus pi to pi, and that is easily seen to be essentially 2 pi times x of 0. So, that is easy to evaluate, you see, by using the inverse discrete time Fourier transform. So, it is essentially this is the inverse discrete time Fourier transform evaluated at n equal to 0 and multiplied by 2 pi. So, that is easy to do. Once you have the samples of the sequence, you have nothing more to do. It is in fact given to you. So, any doubts on this question? Question 3 part B. So, I leave of course the calculations to you. Now, the last question 4 was a very interesting question. In part A, you were given xz equal to e raised to the power z inverse with mod z greater than 0. And you were told that xn was convolved with itself to give y. So, of course, you were asked of course to find out y as a product of x and another sequence g. So, you were told that y, which is the convolution of x with itself, should be written as the product also of x with another sequence g. Now that's easy to do because when you convolve the sequence x with itself, the z transform is multiplied. So you get yz is equal to xz the whole square, and therefore yz is simply e raised to the power 2z inverse with the same region of convergence, mod z greater than 0. And just as you can expand e raised to the power z inverse, you can also expand e raised to the power 2z inverse. That's very easy to do, and that gives you yn is essentially summation n going from 0 to infinity 2 raised to the power of n by n factorial, where 0 factorial is 1, 1 factorial is 1, and n factorial is n by into n minus 1 factorial for n greater than 1. Now this is from the Taylor series expansion. The Taylor series expansion on e raised to the power of x. We have discussed this in the class. We have discussed this as an example of irrational z transforms, and we essentially need to use the Taylor series expansion. And interestingly, this expression here is clearly xn times 2 raised to the power of n. Now, you know, xn itself is, of course, I mean, I must make a correction here. It's the not summation n going. You see, this is 2 raised to the power of n by n factorial un. That's how you must write it. There's a correction here because, you know, you're not writing the z transform, you're writing the expression sample by sample. So y of n is 2 raised to the power of n by n factorial un, where of course the factorial is defined in this way. And what I wrote initially was essentially the z transform, yz, and there I should have written a z to the power minus n. But nevertheless, if I remove the 2 to the power of n here, what I have left, namely un by n factorial. So 1 by n factorial un was xn, the original xn. And so you can see that y of n is xn into 2 raised to the power of n. You can equally well write it as y of n is 2 raised to the power of n times un into xn. Now, therefore, the sequence gn can be specified for n greater than or equal to 0. For n less than 0, the sequence gn can be arbitrary. So, indeed, yn is indeed equal to gn times xn, where gn is clearly specified to be 2 raised to the power of n for n greater than or equal to 0 and arbitrary for n less than 0. You can of course extend it to be 2 raised to the power of n also for n less than 0, it does not matter. But of course, one would give full credit if one has written 2 raised to the power of n. Any acceptable sequence is fine. And the simplest thing that comes to mind is either 2 raised to the power of n itself or 2 raised to the power of n times un. Either of them is what comes to mind immediately, and both of them are acceptable. Now, any doubts about part A of question 4? If not, then we go to the very last of the questions of the mid-semester exam, and that was question 4 part B. And there you were told that there is a system given to you, it's a rational causal LSI system. And the system function was given to you. Hz is 1 by 1 minus a z inverse into 1 minus b z inverse. And a and b are real constants. You don't know whether a and b are equal or not equal, but you know they are real. You don't know whether they are less than 1, greater than 1, nothing else. But of course, you know the system is rational, of course, that's obvious, but it's also causal and LSI, and of course, LSI and rational have to be obvious, otherwise there is no system function. But you know the system is causal. So you know that the region of convergence is very clear, mod z greater than the greater of mod A and mod B. Now, you are given the response in two different experiments. So, two different experiments were conducted. In each of the experiments, the input was of the form r to the power of n for all n. Now, please note, this was r to the power of n for all n, not r to the power of n un. There is a very big difference. R to the power of n un gives a different response, and r to the power of n for all n gives, in fact, r to the power of n. And of course, you know, it is obvious that if you have got a finite output here, we will see in a minute, if you have got a finite output, the r must have been in the region of convergence, otherwise it couldn't have. Let us see. So, what is the output when the input is r to the power of n for all n? In fact, we saw this the very moment we began our discussion on the Z transform. The output would be summation k going from minus to plus infinity hk r to the power n minus k, where hn is the impulse response. And we can split this, r to the power n minus k is r to the power n into r to the power minus k. So, that can be written as r to the power of n times summation k going from minus to plus infinity hk r to the power minus k. And lo and behold, this is nothing but hz evaluated at z equal to r. So, essentially this illustrates the idea of what are called eigen sequences. R to the power of n is an eigen sequence of the LSI system. It goes into the system and is multiplied by a constant, no other change takes place. So, you see, moreover, the constant by which it is multiplied is the value of the z or the system function evaluated at z equal to r. Needless to say, r must be in the region of convergence, otherwise this is not acceptable. You know, this would not converge otherwise. So, r must be in the region of convergence. And you are given two different cases here. You are given the case r equal to 1 and r equal to 4. And you were told that the sample y0 was equal to 3 for r equal to 1. And for r equal to 4, the sample y0 was 96 by 77. So, obviously, we have two equations on the two unknowns a and b, because you can substitute r equal to 1 and r equal to 4 in the x. So, you have 1 by 1 minus a times 1 inverse into 1 minus b times 1 inverse is equal to 3. You see, remember, y of 0 is r to the power 0 times h evaluated at 1. This is for r equal to 1. So, y of 0 is simply h of 1 here for r equal to 1. This is the first equation that you get. And the second equation that you get when r is equal to 4 is that 1 by 1 minus a into 4 inverse into 1 minus b into 4 inverse is 96 by 77. Because y of 0 here would come out to be 4 to the power 0 times h of 4. So, you see, you have two equations in two unknowns, and you can now solve them. Let me write down the two equations that we have once again. The first equation is 1 minus a into 1 minus b is 1 by 3, and the second equation is 1 minus a by 4 into 1 minus b by 4 is 77 by 96. Now, these are essentially, you could treat them as quadratic in either a or in b. So, one can solve these by a quadratic. So, you need to eliminate one of them and you get two solutions. You might wonder why you get a quadratic. Well, you get two solutions because a and b are symmetric. They can be, the roles of a and b can be reversed. So, the two solutions of a are in fact the solutions of a and b, or the two solutions of b, when you obtain them, are in fact the solutions of b and a. That is why you get a quadratic. Of course, needless to say here, it would not have mattered whether a is equal to b or a is unequal to b. That can be obtained once you solve the quadratic. So, you were required to find the constants a and b, which you could, and it turns out that the constants evaluate to 1/3 and half. So, you can take either of them to be 1/3 and the other to be half, does not matter, they are symmetric. Now, of course, I do understand a lot of people took the input to be r to the power of n un, and of course, that was incorrect, that gives a totally different response. Now, this question was meant to illustrate or to test or to strengthen the idea of the Z transform. What exactly is the Z transform? What significance does it have? That was being examined in this question. Any questions on this? So, the question is what exactly did we mean when we talked about symmetry? Well, the role of A and B is indistinguishable here. So, it could be what you are calling B could be A, and in that case what you are calling A would become B. So, A and B are indistinguishable in this. In that sense, there is a symmetry with A and B. Yes, any other questions? So, the question is, could you write r raised to the power of n as r raised to the power of n un plus r raised to the power of n u of minus n minus 1? Yes, you can, but it would not offer any significant advantage. You could do that, but it only makes matters more difficult. It does not simplify matters in any way. Yes, please. Yes. So, the very good. So, the question is, if you did indeed write r to the power of n as r raised to the power of n un plus r raised to the power of n u minus n minus 1, how would you deal with it? That is exactly the problem. R raised to the power of n has no Z transform, or has no Z transform in the sense of conventional functions. You will need to introduce impulses in the Z domain to take the Z transform of r raised to the power of n. So, even when you take r raised to the power of n and un and r raised to the power of n u minus n minus 1 separately, the only possibility is that you solve them separately and add, but that is not convenient at all to do. So, you could find the responses individually in the time domain and add them, but that is not in no way is that convenient to do. So, it is interesting, in this case you use the Z transform, but you cannot, the input and the output do not have a Z transform. That is the great secret in this question, and it was meant to really test the fundamentals of the Z transform to the core. To conclude, yeah, any other questions? Yeah, so there is no, if you take them together, there is no region of convergence. So, you cannot deal, either you deal with them separately and add them in the time domain, not in the Z domain, the time domain, or you work it out straight away in time. It was meant. Now, the aim of many questions in this examination was to test understanding at the core. It is often the case that when one comes to a graduate program in electrical engineering in particular, or in any other discipline, one comes with the full assumption that one has dealt with many concepts earlier and not too much is required to review them before an examination of basic nature. Basics in a subject are often so vast that they need review more than once. one often proceeds with weak foundations to construct a strong second story. But it is also useful once in a while to strengthen one's foundation, so that the stories above become more stable. And I do hope that some of the questions in this examination illustrated that one did need to ask some fundamental questions about fundamental concepts in DSP. Thank you.